So today we are talking about format string exploits. We mentioned these bugs a little bit earlier, so let's get started. Also, all the compilation flags for the files we're looking at today are in the C file. I don't think I use any special flags for any of them, but just to make sure, these are the ones I set. Okay, so just quick topics to go over. Project 2 due midnight. I think that's the weekend after break, that Tuesday. I make zero promises to answer any campus-wire posts during break. I hope all TAs and UCAs will be taking time off. That being said, like the weekend we get back, we'll be answering stuff. Hopefully you get your questions all in before that and you started already. Project 1 solutions will be coming out soon. So if you have trouble with the reverse engineering parts and want to know what you missed, or maybe your script just broke on the last step, we'll be doing explanations, and maybe we'll ask one of you guys to see if we can submit your write-up with the name blurred out. And then presentation groups are due tonight. We need every member listed in your submission and 3 potential project ideas. If you don't have a group, submit your ideas anyways, and we'll use it to pair people. If you have a group of 2 people, still submit that, and then we'll try and match you with another group of 2 or with a single person. Is there any questions on any of this? Yeah?
How fleshed out are you looking for the project ideas?
So I'm going to use Eamon's group as an example because I saw the submission. You did a certain client for a game you want to do, and what were the other 2?
I think one was just like single player game hacking, and then the last one was like Spectre CPU bugs.
So the Spectre CPU bug is specific enough that it's good. But if you do something as vague as game hacking, you'll probably choose the topic in that for you. A lot of people did malware analysis, right? If you just say malware analysis, and we have like 2 or 3 groups that want to do that, I'll probably choose a specific field for you to look at, right? So maybe I do automated detection, and I give your group that, and you say malware analysis. So if you want to do something specific, say it, but also don't go super specific. Like, I want to find this exact bug in this exact piece of hardware, not knowing if you can do that. Right? So keep that in mind. Any other questions? Right? Okay. So a quick recap of what we learned for class. We went over return-oriented programming, also known as ROP, where basically as an alternative of writing shellcode as an exploit, we can write a ROP chain, right? Which the entire concept behind this is instead of writing our own code into the program and into memory through like a buffer overflow, we can now just reuse existing code in the program and just continuously jump around to the program to execute that code. And some advantages of that is we no longer need a really big buffer for our shellcode. We may still need a large buffer overflow to like get all the return addresses written, but we don't need like a buffer of 300 bytes anymore, or 60 bytes, whatever you're using. And there's also like the idea that even if there's not useful code in the function, in the program, if it uses like library functions and those are written in the program, we can use that. And eventually we'll learn ideas like if we get pointers to library functions, even if it's not in the actual program itself, those library functions have to be loaded somewhere in memory, and we can jump to those. So we'll learn those techniques, I think, the week after spring break. ROP is like a very hard topic to internalize without doing it. So the next project is pretty much all ROP, and you'll get to do it hands-on. We have a lab with ROP, and after the lab, we'll do an advanced ROP class where we learn more techniques, right? Were there any immediate questions about how it works? Every year it's a little hard to teach, and people kind of just have to be hands-on with it. So any questions? So actually, let me go back. What were some issues with shellcode? Someone tell me with the idea of shellcoding, what were some problems we ran into from an exploitation idea? Like, right? Yeah.
If you don't have like the address of your buffer like in memory, you can't write shellcode for your exploit maybe?
Oh, so you can write shellcode, let's say if you have a guest call, but you can't really do anything if you don't have a pointer to it, right? So that's one issue. Any other issues with buffer overflows? No ideas?
I mean, there's basically one on the side. We need enough space to write the shellcode.
Yep. Okay, so space is a constraint. What are issues with ROP chains? Let's test what people know about. Yeah.
In a dynamically compiled function, you're going to struggle because you don't know where the library functions are stored on the actual machine.
Yep, right. So if we don't have access to library functions, and if the actual program is pretty small, we might not have the gadgets we need to execute code on ROP. So like, what solves this issue? What is the way that we can know where our shellcode is, or where stuff is in memory?
Address leak.
Okay, so memory leaks, right? There's a whole classification of bugs, which on its own doesn't do anything, right? We call them memory leaks. And all it is getting the program to print an address in memory. Not even the data. We just need to know where things are in memory. And this like enables us to do a lot, right? Because if we have an address in memory, if we can leak arbitrary addresses, maybe we leak the address where our shellcode is so we can jump to it later. Or maybe we leak the address of a function so we can know where that code is in memory, and then we can use ROP to execute that code. Okay, so memory leaks are like very important in exploitation. But the issue is it's super hard to find them, right? No one writes this code. No sane person will ever just print pointers unless you're writing a debugger like GDB, right? And if you're looking for bugs in GDB, God bless your soul. So it's like, how do we find these bugs in a way that isn't intended in the program? And something to like be aware of is if you're writing exploits for whatever agency is hiring you or contractor or company, or if you're just doing it for fun, usually where you find memory leaks is not the same program you find buffer overflows, right? Unfortunately. So what will happen is, say we want to test. This is like something I watched a video on, so I won't mention it. Say you want to like hack into a Tesla, right? Remotely. So Tesla has a few interfaces that you can like interact with. It has wireless, it has cellular, it has Bluetooth, it has RFID for your key. It has a bunch of different ways to interact with it. I'm pretty sure there's a USB port somewhere on it you can probably just plug into. But all of those are different programs running segmented apart from each other. But maybe one of them has a buffer overflow, one of them has a memory leak, right? So you need to find bugs in all of these different programs and then find a way to connect them, and that's your exploit. But on its own, none of these programs by itself is exploitable. So you need to keep in mind that like generally, unless like in this class where we give you a program that's written horribly, it's really hard to find these things. But when you do, huge. People will pay you a lot of money for it. So like the last few classes, let's look at some code. This is the Echo program. I gave you guys echo.c. If you want to compile it, run it. As you can see, all it does is printf, asks for some input. You can send it up to 255 bytes, and it'll print it back. Can someone tell me the bug? Yes.
No format string. So
Right?
you could put your own format specifiers.
Yeah. Let me see when I talk about this, right? So sending the buffer directly, and when I say sending, I mean as a printf parameter, right? It means that we can, if you remember how printf works, the first argument is what we call the format specifier, which is just a string where we can do things like %s. So later parameters are used and like injected in that. So if we wanted to print like an integer value, you do %d as the first argument, and then the second argument is the actual integer we're referencing. So when we actually do user input directly like this, we can make the specifiers ourselves, even though the printf doesn't expect any. So let's go to Linux. And I have all these programs already made, so I'll just execute echo. We can put in a normal string like test, and we can see it does exactly what we expect it to. But now let's do something a little funky. Someone give me a format string specifier. Right. Yeah.
%p.
%p. So %p prints a pointer, and suddenly we get like this weird hex value, right? And the program should have just outputted %p if it was coded correctly. But this is like unexpected. What else can we do? Yeah.
%n.
%n. We're skipping that one. Next one. Someone else. He took the class already. He's cheating. That's another one. Yeah.
Percent D, why not?
Percent D. So we can do. I think that's decimal, right? In 2660, I'm pretty sure that's the same value as this as hex.
Yeah.
But like, do we really understand what this A70 is supposed to be? Like, it looks like a kind of random variable. It doesn't look like anything interesting. Eamon?
How about percent P 2 times?
Oh yeah. Okay, so we're going to do percent P 2 times. I'm going to put a period between it just so we get the two strings split and it's easier to read. Right? So now this looks a little bit different than what we had previously. I don't actually know why it's not A70. It might be referencing something else, but something that we notice is that we get two different pointers. This one looks like something that's a little bit more interesting. And if we actually look at this one, I'm going to show you something kind of curious about this one. So if I type hex board and then we're going to give it a percent sign, this is basically going to print the ASCII hex value of this character. 25, right? And we see there's a 25 here. So then we're going to also print, let's do P instead, and it's 70. So we see the 70 here, we see the 25. So it looks like it did print our string in some different format. But if we look at like actually what printf is supposed to do, this is supposed to be just printing a pointer. So it looks like we somehow printed a pointer and we controlled the value of that pointer with our input. So that's what we're going to be exploring today. Any questions so far? Yeah.
So if you wanted a pointer, like how do you get a pointer just from the stack that isn't altered
I'll talk
by
about that.
that?
So something, I think is on my next slide. Right, so just like we had right before, we can do percent %p a bunch, and I'll print these random pointers. We haven't looked at what printf does in depth, so we don't really know what we're looking at. But it's safe to assume that these pointers are referenced somewhere in our function stack memory, because what you can see is from the example, we're actually like printing input we gave it, and we know this input's on the stack because we did fgets. So it looks like somehow we're referencing stack data. Okay, safe to assume. So something that, just to note, what printf can do is that we're currently, when we execute echo and we're doing, what's it called? Format string specifiers, we do like percent %p, right? Percent %d, percent %s, whatever you want. You can actually do, I think the notation is percent, we can do like percent $5 $p, which this will get the fifth argument, okay? So you can do in your printf, say like, let's hope this works. Yeah, so say you're doing like a printf call where it's like your format string specifier is whatever, and then you print like argument 1, argument, like 10 arguments, right? And maybe you want to reference these multiple times in your thing, so it prints like argument 1 3 times or whatever. And maybe it's like out of order of your arguments. You can actually specify which argument you want to be used at that given time, right? And the way you do that is like print, if I want arg5, right? Print arg5 as like a decimal number, then I do, what is it, percent %5, and then we specify pointer in this case, right? So it's a way for us to mix up the order without having like to pass the parameters in direct order. And there's various reasons you want to do this. Printf is an overly complex and overly overloaded function. Any questions on that? And we can see, just real quick, if I run it with the 5 versus just the normal percent %p, we get different values, probably different values on the stack. We haven't really explored that yet. And like reasons you may want to do this is because like the alternative to this, what we were doing beforehand, is just doing percent %p 5 times, right? And then reading the fifth output. So this saves you like a lot of bytes in your string format specifier. So maybe you can only write like 10 bytes of buffer, and your entire format string payload has to be 10 bytes. Then this saves you a lot, and it makes your life a lot easier. And we'll see other use cases later where this is really important. So one last format string specifier that is built in for some reason that Ibrahima mentioned is %n. So right, all the other ones have to do with printing something. %p prints a pointer, d decimal, x hex. You can do %s and do strings and then reference strings. %n actually writes data. So I think it's like to allocate buffers usually, or like keep a track of like where files maybe you're writing to. Honestly, I can't tell you why people do this. But %n takes the amount of data written out to the console so far in its printf call, and then we'll write it to the next address it references. Okay. So if I do, in this example, print AAA %n, and then I pass this as the argument for n, in a normal printf call, we're not explaining anything here, this is how you write it in real code, it'll write 4 to this address, because we've written 4 bytes right before the %n. So if we were to do %, this is like maybe a little reason why people use it. If we do % as %n, and then like the arguments are name, address. You can think like if this is a program that prints out usernames and maybe like the name, like we have spacing for like to make it look nice in our console. We like keep things consistent spacing. That might be why you use %n to keep track of how many bytes you've already written and then how many white space bytes you need to align everything. That's really the only use case for this in the real world. But here, right, the first address will be name, and then we can write out how long, like, you could use stir length, right, instead of this, but this is a way to do this with printf for keeping track of console output. Does this make sense as you can write values arbitrarily with printf calls, okay?
So wait, in this case, does it write the address into the name?
It writes the previous, so we consider this % string, right? It will write the length of this string to this address, right? Because this is the length of the previously written data, okay? Which is really weird. It's really weird that an IO function can do integer writes to arbitrary memory locations, okay? And who's used printf in CS230? Everyone, right? So probably, like I keep saying, go back to your CS230 projects and see if you just call printf like this. Probably most of you do, right? And if the user gave bad input, then they could get arbitrary memory leaks or memory writes now, okay? And you'll see what this leads to. Like, literally worst case scenario is you just have a while loop that has some printf based off user data, and you can just keep writing shellcode with this, right? You can just write all your code, get all the memory leaks you want, and this is like a full vulnerability in its own. But you need to be able to call this multiple times.
No.
What?
You don't. It just gets a lot harder.
Oh yeah, well, I'm assuming normal constraints.
No, even if a single printf call is already enough for full exploitation.
Well, okay, yeah. So Gilbert is saying like, so we've been looking at like tame examples where it's 1% n, and this is like real world use case. But then like if we're exploiting something, we can, if our buffer is large enough, right? We can like write %n like 100 times and then have like 100 memory writes. Okay. As long as your like payload is like cool enough, you can basically write all your shellcode in one printf function. And that's some stuff we're going to be exploring. So this is all good, but raise of hands, who actually understands how printf works? Right? It's not like a normal function. It can take infinite arguments. Does anyone want to guess how infinite arguments works in C? I will say, we did not know this last year. We looked this up during last year's lecture. Yeah.
It's not kind of like how so you have the registers taking in arguments, but then it also pushes more onto the stack, and the registers then get pushed, and then they pop those and take the arguments again. They just do it as long as they need to.
Okay, so then so you're saying like, okay, if we have more than 6 variables, we push them on the stack like a normal function. Okay, that's an idea. But then like, how do you tell how many arguments there are? We're not passing a parameter that says how many arguments. Yep.
Is it a macro function?
Not really. If you look at printf is like very convoluted, and there's a bunch of libc wrappers, which you could maybe say that's a macro, and what we're actually calling is a wrapper. But like every libc function is to some degree. So we need a clever way of keeping track of the amount of arguments that should be passed.
C defines vargs
and a count, and it's a separate array somewhere for variadic functions?
I don't think in this instance. This is like a weird class. There are other functions like printf that take infinite, or like, I shouldn't say infinite, undetermined amount of variables, right? And we don't pass an arg length. So you have to determine the amount of variables during runtime, which is really weird. But there's certain considerations. So let's, I think I mentioned it on a slide. No, okay. We're going to skip this. So the way it does it, which we discovered last lecture, or last year's lecture, midway through class, because none of us knew how, was if we have our stack, right? Let's say like we're in main right now, and this is the function stack. And we have like random data, like return address, right? Base pointer, we don't really care about any of this. Some random stuff. So say we want to make a printf call, right? We use the 6 registers we usually do with function calling. And like you said, any registers beyond that, we just push the stack, right? So maybe like there's 6 registers that are used during normal function calling. It goes like what? RDI, RSI, RDX, RCX, R8, R9, right? And then say we want like arg 7, 8, 9, 10, right? So I'll write arg 10 on stack here, arg 9, 8, 7. And these are the other arguments that we need for a printf call. And then, the stack stops here, so RSP's here, and we want to do a printf call. Well, printf has no idea that these arguments are on the stack. All it has is the registers you are passing to it. So it does the clever thing of just pushing all the registers to the stack and then just hoping all your parameters are on the stack, right? And it just says anything you pass me, I will consider an argument to be used in the future, right? So the first thing printf does is push all of these in reverse order. So you get R9, R8, right, all the way down to RDI. Okay, and then the way it knows when to access these and if to access them is the first parameter, like we have in this code. The first parameter is always our format string specifier, okay? So if we print, like in this code, if we just send it test, it'll print this as a string, right? There's no other arguments that are needed, and it works fine. If instead we print %s, it'll take that %s as the RDI argument, and then since it starts parsing RDI, it notices that there's a %s there, and assumes there's going to be one more argument, right? So then it'll read the next argument up on the stack, which in this case is RSI. But notice if we here don't pass it more arguments, it's just going to take the register value no matter what it is, okay? So let's actually load echo in GDB and we can see this happen. I'm just going to break out main, and we can run it and disassemble, and we can see what's happening. All right, so we'll disassemble it. And what we want to do is break right at the printf call, okay? And we'll run it. And you can see, sorry, continue. We'll give it the input test like we were previously. And you can see we're just broken at the printf call. The first argument, column debug tells you it, right? The format we were talking about is just test right now. So we can see there's no format string specifiers in this. So it shouldn't print anything interesting besides test. And if we hit continue, run a function, that's exactly what happens. So let's run again and then continue it, and we're going to give it %p this time. Okay, so when we are right before the call, you can see we're broken on this call printf. The format is now %p. This is our RDI register, and you can see DD40 matches with the RDI register here, DD40. So what do we think this will print? Based off how we know it handles arguments, there's one format string specifier. What will this print? Yeah.
Print 1.
Print 1?
RDT register.
Sorry, say that again. It'll print
the value in the RBP register
RBP.
above RSP.
No. Well, okay. So you're saying in this
Yeah, I'm
instance,
looking down there.
right? So also notice that when I say it pushes everything to the stack, it's much more complicated than this, but this is the easy way to think about it. Because printf does have to have its own function data. So I don't know. No one knows how in this class, but it somehow virtualizes its own stack for this. Maybe it pushes everything else and then does its own stack data. But yeah, so we'll say like the new RSP when we're in the printf calls here, right? And this we know is the %p, right? We push it to stack. So what will the %p be reading from?
The one above,
The one above, which is
RDX.
RSI, right?
Oh, is it below on the register?
Yeah, so this is just listing the registers in an arbitrary order, but the actual ones we use for calling functions is this order. Okay. So this %p should be reading from what register? Someone said it? RSI. Right.
OXE7.
Right. So suddenly, I don't know why, but in this function, RSI is set to A70, which we saw earlier with our %p, right? So if we assume printf is working how it should, we should get A70. It'll be equal to. And we do. Okay. Let's run it one more time. We'll hit continue. We'll do %p like 5 times, right? And we'll note the register values right before. So, right, continue the right place, yeah. So RSI currently is set to 0x2e70, right? And then what's next? RDX, 0xFBAD, and then RCX, x55555, right? And R8, 0, R9, 0. So this is exactly what we should expect when hitting continue, right? Well, let's do that. And does it match? Exactly, right? So suddenly, with one controlled buffer, with a bad printf call, we can dump all the registers. And if I was to do more %ps, because like how we talked before, it would assume that we're no longer doing these registers, but we're now pushing stuff that was previously pushed to stack. Printf assumes that if we're calling it in the right context, it'll previously push stuff to the stack, right? So that means, let me run it one more time. Continue. We'll do %p just a bunch of times. We are now printing stack memory. So you can see the last few values are all 72.5, right? For like the last 3 pointers. And that's all the %ps we're pushing, right? That's the actual data. So eventually, not only is our printf popping values off the stack, it's reading the data that we wrote, right, in our buffer. So we can actually have printf reference data that we put in the buffer, which is interesting because we can use addresses in printf to also write data, right? Is people starting to see the trick here? Great, okay. So where are we on the slides now? Just high-level overview. We can now leave values on the stack, spamming a bunch of %ps. We can also do %s, %x, %d. The reason why s is sometimes bad is because strings are terminated with null bytes, and in memory there's always null bytes, right? So you might not get all the data you want from that. That's why %p is usually much safer to use. If you do %s and then it gets a bad address or something, sometimes it'll just segfault, so you have to be wary of that. And then we can also write values to memory using %n. We haven't. I think the demo for that is. We can do that demo now if you want. Which one do I want to do? Also, I gave you a stackleak.c, which actually we can run through now. So you can see this code. Stackleak.c. We set some values on stack. So maybe you didn't believe me that like we can view too many things on the stack. All we did was print the buffer that we gave it. So maybe there's actual like other values on the stack that we haven't seen we have access to. So in this case, it reads a buffer like last time, has the bad printf call, but I gave you some other variables that we're going to try to leak right now. So let's run it in GDB. We'll again break at main, run it, disassemble main so we get the offset of the printf. I'll just break right at the printf call, right? So what do we want to read? We want to read, I think it's called this. We want to read some integers, so if we get anything that prints 5, 3, or 1, roughly in hex, we know we leak stack data. And you can continue this idea to say, look, if we're leaking arguments on the stack, we can also leak base pointer and return address. So we can get like, addresses of places in code and different memory locations that are previously used in higher up functions. So let's run it, continue. It expects input. So again, we're just going to spam %p. And we need to do like at least 6 or something because it pushes the arguments and the rest should be pure stack data. So let's see if this worked. I don't think it printed yet. No. Okay, so you can see I didn't put protections on, so it actually reordered the buffer to be higher up on the stack. But here's the 5 from the 1 int, and here's the 3 and 1. And they just did it because I think those are shorts and they're 4 bytes and not 8. So we completely leaked all the stack data. And you can see the rest of the buffer is here. And that just means that probably the integers are stored here and the input buffer's here. Because remember, we talked about sometimes the compiler will move buffers to the top in case of overflows. Right? We'll see in the next lecture, where we talk about defense mechanisms, leaks for stack memory is insanely huge. Right? There are defense mechanisms that try to protect things on the stack, and if we can leak those, it's very important. Okay. So, how does this help? Yeah.
Could you explain the reason why there's so many 7025s?
Okay, so let me
Just try to.
Yeah, let me run it and continue, and I'll just show you. So this is the payload we're sending it, right? This gets call. If we actually, if you pull up the code, I'll send it, and then, right, all this payload is being stored in this buffer. And this is on the stack. So if we're printing stack data, eventually we're going to print this buffer out, right? Mm-hmm. So if we actually look at the stack from Pwn debug, we can see started like 8 bytes or 16 bytes above RSP is all the %Ps we wrote. And if we print the hexadecimal values of like these characters, that's the 725.
Okay.
Right. Where is it? Yeah, all these 725s we're printing is actually this part of the stack.
Yeah, what about the 2e bit? Oh, that's probably good.
Mm-hmm.
What's the 2e? 7?
The 2e is probably the dot we're putting. Yeah. Okay. Any questions about this? Yeah.
I think you said you were going to show the %n.
Yeah, we can do that as the next demo.
That was my question.
Okay. All right. Because the %n you'll actually. So project 3 is on ROP and format strings, I believe, right? I think you have to do writes with format strings for challenge 3 on the next project, so keep that in mind. So let's check out write.c. Okay, this one's slightly different. We actually get a pointer this time. So we have a buffer we can read to with the fgets and printf like normal, but right before the printf, or the fgets, sorry, we actually printed the address of this variable. Okay, so we're going to try overwrite this variable using printf. I sent you guys a template code, so let's actually write the exploit live, okay? So I'm just going to get it all set up in GDB. So let's walk through what we would need to do theoretically to write to this address. Does anyone have the first idea what we should do? Yeah.
Need to get that output of that first printf.
Yep. So let's just do a data equals p dot read line. I'm going to live debug, so we'll see how that goes. Let me just see I'm parsing it right. Sorry. Okay. Okay, so we can see, if you look here, we actually got this address just from the first read line, so I'm just going to do some extra decoding. Decode, this should turn it into a string, and then strip, I believe, gets rid of the new line. And we'll just run it again and see if that works. Yeah, okay. So we'll read data. It's now a string, so now we're just going to wrap it as an integer, right? This should work. And we'll change the name of the variable to... Okay, so now we should have that stored. What is the next thing we need to do? While someone thinks of it, I'm just going to make sure this works. Anyone have an idea of the next thing? Yep, okay, so that's works. Okay, well, let's think about it, right? So eventually, we want a print end somewhere, right? Our payload has to have at least one print end to change the value. So we put our payload here. We need some print n or percent n, and percent n is going to take the data previously written, or the amount of data previously written as the value to write. We don't really care in this instance what it is. We're just trying to see that we can do it right. So in this instance, I'm just going to add 4 A's to my payload, right? And then we'll put like a percent n. So when printf encounters this, these 4 A's percent n, it's now going to take this percent n is going to look for the next value in the stack and write 4 bytes to it, or the number 4 to it, because the printf should have previously outputted 4 bytes of data, right? Does this make sense? Okay. So now the question is, right? We need this percent n to point to a write me. And how do we properly know where this address is? Yeah.
We need to know how high is it up in the stack.
Yes. So we're going to do my favorite method of exploitation, guessing and checking. So what is it to do the offset? Isn't it like $5? And we're just going to do the P right now because we don't actually care about writing. We're just trying to find offsets. So a good way to find where data is in the stack is just printing pointers until you find it. So we currently print the payload and we run interactive. So let's do this and then we hit continue. Great, actually this is perfect. So we can see from the output of this program, it's a little messy down here, but this is the address that we'll eventually need to do. Write me was not changed, it's still 0. But this is what the program output, right? So my random guess of %5 $p exactly pointed to the right stack value we need. Okay? If I did 4, it would probably be garbage, right? If I hit continue, oh, why is it? Gilbert? Ideas? 4 and 5 is giving me the same value for stack offset. Well, anyways, it still works. Won't question it. But
what's the significance of the number then? If I'm just curious, why do you have to do the 4 A's and then?
It might be that the registers are, for some reason, both pointing to this. So let me just change it to like %8, and that probably, because sometimes registers point to the same data, and that might just be a special case. They really shouldn't be doing this. Huh. Okay, maybe it's just. Let's change it to B's and see if that changes it. Okay, we're getting the pointer no matter what, so I'm not going to question. Yeah?
Is it actually printing the pointer, or is that just the thing printing the buffer?
The only print I have is this write me and then interacted. So actually, let me read the code. Did I have it print the buffer? Oh, yeah, you're right. Okay. Yeah, I was wrong. I was very wrong. So what's happening is it's printing the buffer. Good catch. And it just happens to be that every time I've done %p, it points as null, and it looks like it's doing it right. So what I'm going to do instead is get rid of this, and we're just going to put a bunch of p's. Right, and this should be more consistent with what we're looking at. Thank you for that. Right, so what this should do now is send this payload of A's and %P's. It will print it, but during that print, it will actually run the %P's, and we'll see, yeah, now it looks better. So now we're printing different values on the stack. Right, we can see our original payload, and then it's injecting the pointer data for all of these. And something that you can note or keep track of is that it will always have these 6 registers, always push, right? The first 6 we do from printf will always be these registers, because printf just assumes that it'll push the data you need on the stack. So usually we don't get stack data if this $ indexing is less than 6. It's just the way to do this fast. But what we want to do is keep adding %P's. It sounds bad, but this is exactly what we want to do, because we want to find which one references the start of our buffer, right? Which one of these will print the A's. So I'll go run it one more time. I'm just going to hit continue PDB. Is this really not enough? No, this definitely should be. Okay, yeah. So you can see 41, 42, 42, 41. These are actually the A's and B's of our original payload. So we actually overshot this a little bit. We overshot this by 6. So let's get rid of some, right? And this is kind of what your exploitation looks like. If you're going to be doing this for the project, you just kind of screw around until it works, right? So we can see currently we have 7 P's, and I'm just going to keep those there for now. But what we're going to do is we're going to do the A's and B's just so we can keep reference, right? But then we're going to add the address of write me, right? And we're going to see if we can actually get these %P's to print that address, right? Because if we can have a %P reference it and get that data, then we can get a %N to reference that data, right? And we can use it as a valid offset to write to. So I'm just going to add this to my payload real quick. All right, any questions so far? Okay. So you can see here the %P's printed some random data. And it got all the A's and then what looks like nothing. And the reason why this looks like nothing is because it's actually the write me address. So we got the %P's to now print out the write me address, which is very useful because now we can replace one of those %P's with a %N and I'll write to it.
What's the point of all the A's then?
The A's is just something we can put in the buffer and then mess around with %P's to know where we are in the stack. Because when we print all the 4 ones and the %P's, we pretty much are exactly sure that's where we are.
Because if we removed all the A's, wouldn't it be automatic at the start?
Why is it not? Oh, I know. Okay, I actually have to put the write me after because, like I was saying, null bytes screw things up. I think is the issue here.
It's write me address, not write to.
Okay. Also, I might just release, so we can see here we have all the 4 ones. So right, this second to last P is printing all our A's. And then the next P is printing, these actual characters. And then since we have the address after, we can see the address starting to be printed here. So I don't think I actually have time to finish this. I can release a script that does it and people can look over it because we have more stuff I want to talk about in this class. But basically the methodology is you keep doing these %Ps until you get to a location in the stack you want to write this write me address to, right? So if we got this write me address at the very end to be 8-byte aligned, then we can then index it with a %n using the $sign, and we can trigger a write. As a general concept, does this make sense? Any questions about that? Yeah.
If you have to be 8-byte aligned, how do you write a value bigger than 256? Right?
Okay, so this is a good question. The address has to be 8-byte aligned because you're referencing a pointer, right? If you're referencing something as a pointer, it will always have to be 8-byte aligned. If you want to write, say we want to change this write to me as like the address of main. Mm-hmm. We're not going to be able to output like billions of characters to put that value. Well, printf also has the H%, right? Which you can tag onto things and it counts as half. So if I want to write a short integer versus an integer, I do HD and it stands for half, right? And then I can do HHD and it'll only do 1 byte. And in reverse, I can do LD, which stands for long, and it'll double the length. Same thing for writes. So if I do HHN, it'll only write 1 or 2 bytes, giving how many H's I put. So what you can do is if you have a loop, or even if you just do multiple %Ns in your payload, you can tag on H's and write 1 byte at a time. And then if you're writing 1 byte, say you want to set it to, like 128, but the next one's 63. If you go over 256, it'll loop back under, right? So that's how you would do a full pointer write. Okay. So let's talk about ELF files a little bit more, right? Like I previously mentioned, for raw, program can be compiled statically or dynamically, okay? If a program is compiled statically, then all the libc functions are self-contained in it, which means we can send it around, great, but the function's huge now. The entire program is going to be, millions, billions of bytes longer, which is a problem with the older internet and bandwidth. Not so much now, but still generally, you don't want to do that. If it's compiled dynamically, then we know the library somewhere on our machine that we're running it, and that library is going to be loaded in memory somewhere. So we can just access that library in memory. Generally, we don't want user programs to be able to call other programs, and libc is just a program when you think about it, right? Library functions are just programs running. So what we do is, if you remember how we talked about virtualized memory, if this is our virtual memory layout, where like this is 0, and this is like the top of your memory range, right? We just, like we say, we load code in specific regions, we'll load libraries in specific regions. So maybe we say like, this part of memory is where libc functions are. And if your user program accesses this, then the kernel knows you're trying to access libc functions, and will like do kernel segmentation virtualization stuff to get you to that libc code, okay? Now, if we talk about how code actually runs in this, if a program's compiled statically, if we want to call functions, we have set addresses, right? Main's always going to be in this location if it's pre-compiled. If we have fgets actually existing in our program, we know exactly where fgets is, right? So we can just call that address. If it's statically linked, then exploitation is really easy. We saw that ROP, we can use gadgets from fgets if it's already in the program, right? We can have all that reuse codes. We don't need memory leaks. Everything we've done so far with ROP has not needed memory leaks, and that's great. The only memory leaks we would have needed is the address to like a buffer, because that's memory, not program code. Okay. Any questions on statically linked? They're pretty simple. It's how programs should work if you just think about it naively. But operating systems make your life much harder. Okay. So dynamically linked programs are really complex. Okay. How do you actually know where code from another function is, right? And it's not like we can just say, like, if we disassemble something, if we just GDB the echo function, right, and then we disassemble main, we have these calls where we just like call a hard-coded address, okay? How do we actually know where to call if we're doing libc functions that aren't part of our program? And it's really up to the kernel to just put them anywhere. So our user land programs don't know what to do with them. The way you do this is remember how we said like main isn't actually the first thing to be called? There's this whole other section called the dynamic linker, right? And this is actually its own executable, right? So if your operating system wants to start a program, it actually works with this program called the dynamic linker, where it'll pull offsets, locations in libc for like global variables, functions, and it'll tell this new process that's starting where all this data is, right? So the kernel kind of runs with this like dynamic linker program to tell the new user land program where all this information is, right? But then you ask, like, how do we actually, like, our main function, we don't want to update the actual code in real time, right? That still seems bad. We don't want to have to rewrite every call function in our already compiled program where we may not have source to all these libc offsets. So we want to have the dynamic linker write this in memory. So let's see how like ELF files actually deal with this. So introducing PLT and GOT. Like we were saying, ELF has things called sections, like .text is program code, .data, .bss is like global variables. .plt and .got are also sections. PLT stands for procedural linkage table. GOT stands for global offset table. This is a very convoluted way to add functions to your program, and no one can really tell you why, or I'm sure people can, I cannot, tell you why it's like this, right? If you really want to learn how it works, I could send you like quite literally a 20-part article series. Basically, all you need to know is there's two sections, right? PLT and GOT. These are all slightly code, slightly memory regions, right? So say we want to call a function. If you go to the GOT PLT code I gave you guys, let me just exit everything. Right, all this is the function that we're looking at, but I compiled it to be dynamic, right? So this will actually run the dynamic linker and look at libc files. If we run it in GDB and we disassemble main, you can see when we call fgets here, we're actually calling fgets at PLT, right? This is a little nuance. So the end goal is to call fgets, but we're not directly calling fgets because we don't know where it is. We're going to call the procedural linkage table. And what this does is, if we want to reference a libc function, we first go here. And like it says, it procedurally links functions. The reason why we don't do all this linking at the very start and why it's procedural is because say we have a program with like tens of thousands of libc functions used, or maybe even like hundreds of thousands. You don't want to load those all in program start because that'll take a lot of time, right? So you only want to do it when you need it because you probably won't even use a lot of these functions unless you hit like really weird code branches and they're like edge case functions, right? So you want to do this all only when you need it. So you go to the PLT, and the PLT has no data. I actually pulled it up in Ghidra. So if you want to look at Ghidra, you can actually look at these sections. The window I'm going to pull up is very small, but I'll tell you what you need to look at. So this is the PLT. You want to look at the assembly. The disassembly makes no sense. All this looks like is some random push, some random jumps, right? Here's a push 0 jump. Here's a push 1 jump. Here's a push 2 jump. And notice all these jumps go to the same place. It looks like a very weird segment in your memory, right? So what it does is it's basically a function lookup table. Okay, and if the function doesn't already exist, we haven't queried the dynamic linker yet. Then it just pushes the offset of the function. So like you have a array of functions, and maybe like this one's fgets, this is printf, and you can think of these all as addresses to libc functions. If it's not populated left yet, then we just push the offset and call the global offset table. Right, that's all it does. And you can actually, if we run the program in Cone Debug, notice I haven't called any of these functions yet. I just started the program. You can run the command GOT. Well, I have to break main and then run GOT. This lists the functions that need to be dynamically linked. You can see it says at glibc, but it gives us like addresses that are in our program already. Like, and you can see they differ by 16 bytes, and they don't look very interesting, right? So this is the unpopulated data, right? So what happens is PLT sees that it's unpopulated, jumps to the GOT, and then GOT also notices that it's unpopulated, calls the dynamic linker with the right information, and then it'll fill in the fget section, right? At libc, right? And what happens is there's two sections. I don't really know why there are sections, because what happens is PLT jumps to GOT, GOT populates and re-jumps back, and then on the next call, when it's already populated, it also jumps to GOT. So I don't quite understand why it doesn't just go directly to the global offset table. There's probably some linker theory stuff. You don't really care. But the thing to notice is this address, we have no idea where fgets is so far, right? So what I'm going to do is, this is simple main again. And we're going to break at main plus 51, which is this address, right after fgets, right? So if it works how we should expect it, we should have already ran the fgets call, which means we should have had to query the dynamic linker at some point, and get the actual address there. So we're going to set that breakpoint, continue. I'll just put in the word test. You can now see we broke right after it. And if I run the GOT command again, which just prints the global offset table, you can see that this address is now populated, right? So this is actually the address of where libc is, in the fgets function specifically. And if we run the command vmmap, which stands for virtual memory map again, we can actually see like the dynamic linker LD is loaded in these areas. Some library function libc is loaded in these regions. So fgets 7e is like in this region, right? So we can see the fgets is actually in this virtual map region. GDB always loads this in the same location because it's the debugger and it wants some things to be stable and how it does debugging stuff. But generally these addresses are always random, and you need memory leaks to find out where this code is. Okay. What was your question?
If for this PLT and GOT bit, what's the need of GOT altogether? If it's not existent in PLT, why wouldn't it make more sense to just get it directly from the dynamic link?
The reason I think there's two is because you have to treat code and variables separately, right? Code or variables is something we can just grab. We can just say like dynamic linker, give me this address. And you know, the way we do variables is a little different. You like query the dynamic linker, it sets a register to the value of that variable or the location of it, and then you move that from the register when you want to use it. So if we need code, we need to actually continue executing stuff. We can't just say like dynamic linker, tell me an address, and then we'll run a call on that address. We need to do jumps and returns and call out codes to properly handle functions. So I think that's why the PLT is kind of an extra step. Again, I could send you a 20-piece article if you're really interested, but it's not really necessary. But so think about our exploits, right? This is just some extra stuff. So PLT and GOT are not randomized, just like code. These locations are always constant, up to like offsets from main and stuff, right? So if we can corrupt the PLT and GOT, then we can redirect code execution. So look back at this, right? So fgets we now know is loaded at this location, but the actual address that we need to call, 7FFF, right? This is still a thing in memory. So we can change, if we can get arbitrary memory rights, we can change this number. And then next time fgets is called, it'll call something else. So if we wrote to 404028, the address of our shellcode. Next time fgets is called, it'll actually jump to our shellcode. But notice you have to do this after fgets is populated, or else it'll just query the dynamic linker and overwrite the address you already wrote to, right? So with printf calls, if we have writes, we can overwrite the global offset table and then just jump anywhere. Also note, now that we're getting to dynamic linking, if we know where libc is in memory, we can now use offsets to calculate any libc function. And we can just call system from libc directly. So a little feature of compiled libraries, right? Just like our code, every time we run our code, main, if we have two functions, main and function one, those are always the same offset from each other every time we run the program, right? Because the assembly is constant. Same thing with library functions, right? If we know exactly what library they're using, in this instance, glibc225, there's databases online where I can say, I have this address of fgets. What offset is system from fgets? We can query it and then just maybe change like the last 2, 3, 4 bytes of this, and we can just get a different libc function, right? And there's libc functions that just gives us shells. So instead of writing shellcode, we can just call system directly and run system commands, okay?
So wait, you're saying the offset is fixed always?
Yeah, for libc functions. If you know the exact libc function, there's just tables of offsets that you can Google online. Yeah.
Is there ever a time later on where like the global offset table queries the dynamic linker again to check if the offset is correct?
I don't think so. I mean, it's every time, like, libraries are rarely loaded out of memory. I can't think of a reason why that would happen. I think in that issue, if you have a library that gets unloaded out of memory, that's something wacky going on with the kernel. Because that means every function that uses it, or every program that uses that library, also has to be stopped. So at some point, it's not a user land issue at that point, right? Yeah.
So we don't, for like the system functions that can make a shell, we don't have to wait for those to populate?
No, so libc, whenever we want to load a libc function, just like a normal program, we load the entire library, right? We just don't have offsets to the library. We don't know where it is in virtual memory. So this is a way for us to like query random libc functions if we just know one address to the program. So think about in our exploits with raw shellcoding, and now we have the tools of printf writes, which I'll send the code that does it and explain a little bit more. If we can now overwrite libc or GOT offsets, we can now call any libc function, right? And this is all stemming from basically a memory leak issue. So you can get full code execution with just printf now. You don't need ROP, you don't need shellcode. You just need redirect libc, which is scary, right? These bugs very much do exist. And there's definitely been 0 days in kernels because of these. Because printf also, like, you may think, oh, this is some random C function that, you know, maybe people don't actually use in production or it's not in kernels, but kernels have their own printf version that's basically the same. And there's many functions in Python and different languages that boil down to printf eventually. So there's a lot of scary things. Yeah.
So like a lot of like malware, don't they usually sometimes they inject their own DLLs to like
If we're talking Windows?
Yeah.
Yeah.
So like is it more common for them to do that? Because like I know like a lot of the things I've seen is like they usually use that instead of actually going and trying.
Windows libraries are much more complicated than Linux, and there's reasons you do that versus like most Linux malware doesn't do that. Most Linux malware, what happens is, you know, maybe you get a foothold using one of the bugs we learned in this class, but then if you want to do more things, you look for like misconfigurations on the system for like administrator users and stuff like that. Right? Like malware doesn't
different.
What?
It's not that different.
Malware doesn't often load its